Hello and welcome you all in the problem solving class of the course Principles of Signal and System. I am Vivek Kumar Srivastav, PMRF Research Scholar of Antenna and Microwave Research Laboratory, Indian Institute of Technology, Roper, and TO of this class. So in the previous class we have seen numericals based on the topic discrete time Fourier transform and discrete Fourier transform. So in the today's class we will cover numericals based on the topic discrete time Fourier transform and discrete Fourier transform along with the digital filter. Okay, so let us start. So the first problem is, consider the discrete time Fourier transform x of omega is equals to 1 where omega is less than equals to omega and 0 for omega which is greater than w and less than pi. Okay, so basically here we have to evaluate the inverse dtft. Okay, that is the x of n that we have to evaluate. Okay, for this given x of omega that is given in the problem. Okay, so to solve this problem we can use the expression of inverse dtft. Okay, which is written as x of n is equals to 1 over 2 pi integral minus w to w. Okay, because here the x of omega, so let us first plot the x of omega. Okay, so x of omega, this is the x of omega with respect to omega axis. Okay, so the value will be 1 for the range of minus w to w, and apart from this, okay, that is greater than w, okay, and less than pi, let us say. Okay, because we know that the discrete time Fourier transform is basically defined for the range of minus pi to pi. Okay, so this is basically the time period of x of omega. So the x of omega is 1 here for the range of minus w to w, and for the range w to pi and minus pi to minus w, its value will be 0. So here I am directly taking minus w to w because apart from this range, okay, the value will x of omega will be 0. Okay, so that's why here uh, yeah, its value will be 1 into e raised to the power minus j rho n. Oh sorry, this will be plus j rho n into d rho. Okay, so now we can integrate this. So 1 over 2 pi integral e raised to the power j rho n dot d rho. Okay, and limit is from minus w to w. So now after integration you will get j rho n over jn. Okay, and limit is from minus w to w. So this we can now substitute the limit, that is minus w and w, in this e raised to the power j rho n. Okay, so this will be e raised to the power j w n minus e raised to the power minus j w n over j n. Okay, so now I will take the n as a common here. Okay, and 2 inside this bracket, so this will be 1 over pi n, and this will be e raised to the power j w n minus e raised to the power minus j w n divided by 2j. So this expression is basically for sine of wn. Okay, so this we can further write it as sine of wn over pi n. Okay, so this is basically the x of n. Okay, that is the inverse dtft of this x of omega. So now we in the solution, in these 4 options, we can say that option C is the correct option. Okay, so here is the solution of the previous problem that we have already solved. So now moving to the next problem. Okay, so here the problem states that the input output relationship of an LT linear time invariant discrete time system is given by the following difference equation. Okay, so this input output relation for a linear time invariant discrete time system is given to us. Okay, so on the basis of this difference equation, we have to basically determine here the transfer function and the impulse response of the system. Okay, so uh, here, as we know that this difference equation is given to us, so to determine the transfer function, which basically relates as h of omega is equals to y of omega over x of omega. Okay, this is basically the transfer function of any system. Okay, so basically from here we can see that transfer function is basically a ratio of output of the system to the input applied to the system. Okay, so as the difference equation is given to us, so to determine the relationship between the output of the system over input applied to the system, what we will do here, we will take the DTFT, that is discrete time Fourier transform, on the both side of the this difference equation. Okay, so here we will take DTFT DTFT on both sides of difference equation. Okay, so now uh, let us take the DTFT. Okay, so here we will take we will consider one property of the DTFT, that is the time shifting property. So as we know that if suppose x of n is given to us, okay, which is the input applied to this system. Okay, so if let us suppose the uh, Fourier transform corresponding to this system is x of omega, so for determining the Fourier transform, that is discrete time Fourier transform of the shifted function, okay, what we will do, we will multiply the frequency response by exponential term, that is e raised to the power rho naught minus j n naught rho into x of omega. Okay, so this is basically the shifting property of the discrete time Fourier transform. So here we will use this property first of all. Okay, so let us now solve this difference equation by taking the discrete time Fourier transform on both the sides. Okay, so this, the first term we can write it as e raised to the power j 2 rho into let us suppose the Fourier transform of output function is y of omega. Okay, so now the second term will be 3 by 4 into e raised to the power j omega into y of omega plus 1 over 8 y of omega, okay, is equals to 2 into e raised to the power j omega, sorry, this will be e raised to the power j 2 omega into x of omega. Okay, so now we will take y of omega common here on the left side, so we can further solve it as y of omega into e raised to the power j 2 omega minus 3 by 4 e raised to the power j omega plus 1 over 8 is equals to 2 e raised to the power j 2 rho into x of omega. Okay, so now we can write the transfer function as y of omega over x of omega. Okay, so we will divide this term from both the sides, so this can be written as 2 e raised to the power j 2 omega over e raised to the power j 2 omega minus 3 by 4 e raised to the power j omega plus 1 over 8. Okay, so now we can multiply both the numerator and denominator by this factor, that is uh, e raised to the power minus j 2 rho. Okay, so after multiplying this term on both numerator and denominator, what we will get, 2 over 1 minus 3 by 4 e raised to the power minus j omega plus 1 over 8 e raised to the power minus j 2 omega. Okay, so now we can further uh, uh, so now we can see here that the denominator function is basically having an order of 2. Okay, so we can break this denominator function as, okay, so basically here we can see that denominator is basically having a 2 roots. Okay, so we are now trying to further break it into 2 roots. Okay, so we can further solve this, plus 1 over 8 e raised to the power minus j 2 rho. Okay, so now from here we can say that the 2 roots of this uh, transfer function is basically 1 by 2 minus j rho into 1 minus 1 by 4 e raised to the power minus j rho. So basically these are the 2 roots of this transfer function. Okay, so now we can use the uh, uh, partial partial fraction method. Okay, so as to basically uh, further solve this difference equation in the known form of transfer this Fourier transform. Okay, so for this purpose we can write this h of omega as, first of all, 2 over 1 minus 1 by 2 e raised to the power j rho into 1 minus 1 by 4 e raised to the power j rho. Okay, so now we can write this transfer function as a over 1 by 2 e raised to the power j rho plus b over 1 minus 1 by 4 e raised to the power j rho. Okay, so these are basically the 2 rows. So now we can use the concept of partial fraction. Okay, so as to determine the coefficients, that is a and b. So after, so let us first solve a. Okay, so for that what we will do, we will multiply this root with this transfer function and replace e raised to the power, just a moment, yeah, this will be e raised to the power minus j rho. Okay, yeah, so now we can multiply this root for determining the coefficient a in this transfer function. So we can solve it as 1 minus 1 by 2 e raised to the power minus j rho into 2 over 1 minus 1 by 2 e raised to the power j rho into 1 minus 1 by 4 e raised to the power minus j rho. Okay, so this function will cancel out, and now we can put the value of uh, e raised to the power minus j rho as 1 by 2, or say, sorry, this will be, yeah, so we can put this here. Okay, so after solving you will get the value of a as 4. So similarly you can determine the value of b, okay, for this coefficient. Okay, so once you determine, you will get the value of b as 2. Okay, so now h of omega we can write it as 4 over 1 minus 1 by 2 e raised to the power minus j rho, yeah, plus 2 over 1 minus 1 by 4 e raised to the power minus j rho. Okay, yeah, so here one mistake will is there, so the value of b will be minus 2. Okay, so once you determine the value of b, will be equals to -2. So now we have put the value of a and b here in the expression of transfer function. Okay, so we get this expression. So as we know that uh, a raised to the power k into uk having the discrete time Fourier transform of 1 over 1 minus a e raised to the power j rho minus, basically. Okay, so we will use this standard formula so as to determine the h of k here. Okay, so this will be equals to h of k will be equals to 4 into 1 by 2 raised to the power k into uk minus 2 into 1 by 4 raised to the power k into uk. So this is basically the expression of impulse response of the system. Okay, so now we can use this expression to further plot this h of k, that is the impulse response. So while plotting, what we have to do, we have to first see here that the h of k will be 0. This will be 0 for all k less than 0, that is for all negative value of k, h of k will be equals to 0, because here uk is the function that is multiplied with the both of the terms, okay, of h of k. Whereas for k greater than equals to 0, we can determine the value of h of k by using this expression. Okay, so now you can put the value of k as 0, 1, 2 and 3, and then plot the value of h of k here with respect to k. Okay, so once you plug the value of k as 0, 1, 2, 3 and so on in this expression, you can plot the value of h of k and with respect to k. So after plotting it, you will get this kind of response. Okay, that
Uh,
represent, yes.
Sir, just one question. Can we say this transfer function is causal?
Yes,
Because
because at,
h of k less than 0 is 0, so causal, right?
yes, yes,
Is causal. And we can also do this through Z transform, right? Taking Z transform and then to inverse
yeah,
Z transform.
because we already know that the relationship between z and its discrete time Fourier transform is basically e raised to the power minus j omega. Okay, so either you can use the value of, either you can use the z transform method or discrete time Fourier transform method. You will get the same response basically here.
Okay, sir.
Yeah, so yeah, so after plotting, you will get this kind of response, which is basically represent the impulse response of the linear time invariant discrete time system. Okay, so any doubt in this problem? Okay, so let us move ahead. So the next problem states that plot the magnitude and phase spectra of linear time invariant discrete time system specified in the previous problem. So whatever discrete time uh, that is the transfer function given to us, okay, like this transfer function that we have analyzed, okay, this one. Okay, so this is basically h of omega. Okay, so we have to basically plot the uh, magnitude and phase response of this transfer function here. Okay, so that's what the problem is stating. So here I'm again reading this question for you. Plot the magnitude and phase spectra of linear time invariant discrete time system is specified in the previous problem. So first of all, let let me write this h of omega once for you. So this will be equals to 2 over 1 minus 3 by 4 e raised to the power minus j rho plus 1 by 8 e raised to the power minus j 2 rho. Okay, so this was the transfer function that we have analyzed in the previous problem. Okay, so basically this represents the linear time invariant discrete time system. So for this kind of system we have to plot the magnitude and the phase spectra. Okay, so for uh, uh, plotting the magnitude and phase spectra of this problem, what we have to do, we have to first simplify this h of omega. Okay, so for this purpose we will use the Euler identity, which states that e raised to the power minus j rho, uh, basically, or e raised to the power minus j omega, we can write it as cos of omega minus j sine of omega. Okay, so we will use this identity and we will plug this e raised to the power minus j omega in this expression. Okay, so let me put it here. Okay, so h of omega can be written as 2 over 1 minus 3 by 4 cos of omega minus j sine of omega plus 1 by 8 cos of 2 omega minus j sine of 2 omega. Okay, so we can further solve this h of omega as 2 over 1 minus 3 by 4 cos of omega plus 1 by 8 cos of 2 omega. So here I am just trying to separate the real and the imaginary part that is present in the denominator function. Okay, so plus j over 3 by 4 sine of rho minus 1 by 8 sine of 2 rho. Okay, so this we can say that this can be written as 2 over real part plus j into imaginary part. Okay, so here this function basically represents the real part and this function basically represents the imaginary part. Okay, so now we can determine the magnitude of this h of omega. Okay, so this magnitude we can write it as 2 over under root of, yeah, 2 over under root of real part square plus imaginary part square. So this basically represents the magnitude. Okay, and the phase of h of omega we can write it as, that is the phase of numerator function minus the phase of denominator function. Okay, so this is basically equals to phase of numerator minus phase of denominator. So this we can write it as 0 because in numerator there is no imaginary part. Okay, so that's why the uh, phase of the numerator will be 0 here, whereas the phase of denominator will be minus tan inverse imaginary over real. Okay, so this will be equals to minus tan inverse imaginary part over real part. Okay, so now you can put the value of real and imaginary in both the magnitude spectra and the phase part of this h of omega. Okay, so once you determine the modulus of h of omega, that is the magnitude, and the phase of h of omega, we now have to plug the value of omega. Okay, from minus pi to pi. Okay, so we as we know that this omega is continuous from minus pi to pi here. Okay, so we now put the value of omega here in this expression of magnitude and phase from minus pi to pi, and then we can get the value of magnitude and phase for different values of omega. Okay, so once you get the different value of magnitude and phase at different values of omega, you can now plot the value of magnitude and phase. So once you plot the value of magnitude and phase, so you will get this kind of curve. Okay, so this basically represents the magnitude plot, and whereas this represents the phase plot of the h of omega, that is the linear time invariant discrete time system transfer function. Okay, so I hope this problem uh, was clear to you. So now moving to the next problem. So the next problem states that calculate the 4-point discrete time Fourier transform of the aperiodic sequence, that is x of k, of length n is equals to 4, which is defined as follows. Okay, so this problem basically we have solved in the previous class, so this is just for revision. Okay, and we will also also see one more alternative way to solve this kind of problem. Okay, so first of all, we will see the uh, previous method that we have seen in the previous class. Okay, so that we will see here first of all, and after that we will jump to the alternative method, which is basically the matrix multiplication method of determining the DFT. Okay, so in the previous class we have seen that this kind of uh, uh, Fourier transform, that is discrete Fourier transform, we can evaluate by using the expression of DFT. Okay, which we can written as, yeah, so which we can written as x of r is equals to summation k is equals to 0 to m minus 1 x of k into e raised to the power j, yeah, e raised to the power minus j 2 pi r k over m. Okay, so in the previous class we have seen that how to determine the uh, discrete time Fourier transform of this aperiodic signal that is given in the problem by using this expression. Okay, so let us now resolve it once more, so that it will be clear. Okay, so like here in the problem itself, it states that we have to determine the 4-point discrete Fourier transform, that is the frequency in the Fourier transform, okay, which we have determined from DTFT. We basically have to sample this frequency for four different uh, four different points. Okay, that is n is equals to 4. Okay, so here you can say this as n. Okay, instead of m you can say this is n. Okay, so here n is equals to 4 is given to us, that is 4 sample of frequencies at the output of uh, DFT. Okay, at the output of the system basically. Okay, so we have to determine the coefficient of the samples basically here. Okay, so we can write this x of r for particular to this problem as summation k is equals to 0 to 3 x of k into e raised to the power minus j 2 pi r k over 4. Okay, so now we can further expand this expression, x of 0 plus x of 1 e raised to the power minus j 2 pi r by 4 plus x of 2 e raised to the power minus j 4 pi r by 4 plus x of 3 e raised to the power minus j 8 pi r by 4. Okay, so now we can put the value of x of 0, x of 1, x of 2 and x of 3 from this x of k for different values of k which is given in the problem. So we can now replace this value of coefficients, so the final x of r value that we will get is written as 2 plus 3 e raised to the power minus j pi r by 2 plus, sorry, this will be minus 1 into e raised to the power minus j pi r plus 1 into e raised to the power minus j 2 pi r. Okay, so now to determine the coefficient of the different samples of the output, what we have to do, we have to basically uh, put the value of r from 0 to 3. Okay, because here in the question itself it has been says that we have to determine the 4-point DFT. Okay, so we have to put the value of r as 0, 1, 2 and 3. Okay, so now let us put the value of r as 0, 1, 2 and 3. So x of uh, 0 we can written as 2 plus 3 minus 1 plus 1, which will be equals to 5. Similarly, we can determine the x of 1. Okay, so this will be equals to 2 plus 3 e raised to the power minus j pi by 2 minus e raised to the power minus j 2 pi plus e raised to the power minus j 8 pi. Okay, so now we can solve this. Okay, so once we solve this expression, we will get the final result, that is x of 1 as 3 plus j2, oh sorry, 3 minus j2, 3 minus j2. Similarly, we can put the value of r as 2 and r as 3. Okay, so to determine the value of x of 2 and x of 3, so once we plug the value, so we will get x of 2 as minus 3 and x of 3 as 3 plus j2. So this calculation part I am leaving to you, so later you can plug the value of r as 2 and 3 in this expression so as to get the final 4-point DFT. Okay, so this solution we have already seen in the previous class. Okay, so now we will solve the same problem by using this alternative method, which is basically the matrix multiplication method. Okay, so matrix multiplication, this method is basically coming after the simplification of the same formula that we have seen. So let me rewrite the formula once again. Okay, so x of r is equals to summation, yeah, summation, just a moment, this will be k is equals to 0 to n minus 1 x of n, or say x of k into e raised to the power minus j 2 pi k r over n. Okay, so to obtain this matrix, what people are doing, they just plug the value, uh, or say they expand this x of r as uh, for different value of k, let us put here. So for k is equals to 0, this will be x of 0, x of 1, x of 2 up to x of n minus 1. Okay, similarly for k is okay, so this uh, yeah, actually this, there is a small error here. So x of 0 plus x of 1 into e raised to the power minus j 2 pi r by n plus x of 2 e raised to the power minus j 4 pi r over n plus dot dot plus x of n minus 1 into e raised to the power minus j 2 pi into n minus 1 into r over n. Okay, so this we can get after expanding this, after basically expand this expression of discrete Fourier transform. So now to determine the matrix multiplication, we have to just plug the value of r here in this expression. So now you can see here that once you plug the value of r as 0, so you will get x of 0 plus x of 1, because here r is 0, so this exponential term will be equals to 1 for all the terms. Okay, so the final expression that you get for x of 0 will be equals to x of 0 plus x of 1, x of 2, x of 3, and so on up to x of n minus 1. Okay, so the summation of all this value will be equals to capital X of 0. Similarly, you can put the value of r as 1 so as to determine the second expression. Okay, and so on. Okay, so that's how you will get the this matrix basically. Okay, so now this matrix basically represents the discrete time Fourier discrete Fourier coefficient. Okay, so this matrix basically represents the discrete Fourier coefficient that we can see here in on the left side of this matrix multiplication, which can be computed by multiplying the discrete time sequence x of k, which we can see here, arranged in the column vector in ascending order of x with respect to the time index k by the discrete Fourier transform matrix F. Okay, so this statement basically says that by using this matrix, okay, we can determine the discrete Fourier coefficient, okay, by just multiplying the uh, uh, discrete sequence that is given to us with the discrete Fourier transform matrix. Okay, so here is the discrete Fourier transform matrix. Okay, so directly by multiplying these two, we can easily determine the discrete Fourier coefficient. Okay, so let us now solve the same problem here once again. Okay, by using this matrix multiplication technique. Okay, so he in the problem itself, it says that x is equals to 2 3 minus 1 and 1. Okay, so this input sequence is basically given to us. Okay, so as in the question itself, it states that we have to determine the 4-point DFT. Okay, it means that we have to determine only x of 0, x of 1, x of 2, x of 3. Okay, so only these four coefficient we have to determine. So corresponding to these four coefficient, the DFT matrix will be equal to this. Okay, and we have to now take the matrix multiplication of this DFT matrix with the input sequence that is given to us. Okay, so once you multiply this matrix, okay, so the final response that you will get will be remains the same. Okay, so like in the previous problem we have got the same expression. So like here you can see that for the x of 0 we get 5, x of 1 we get 3 minus j2, x of 2 minus 3, x of 3 3 plus j2. So the same uh, value of coefficient we have got by using this uh, yeah, matrix multiplication. Okay, so one may ask that if suppose we can directly get the value of discrete time discrete Fourier transform by using the expression, then what is basically the need of this matrix multiplication? Okay, so here like for example we have taken the uh, discrete Fourier transform only for 4 samples. Okay, but in practice the sample will be very high. Okay, so that we cannot determine by using the expression. Okay, so for that we have to use some specific tool like MATLAB is there. Okay, so MATLAB basically works on matrix as we all know. Okay, so we can directly define this matrix and this input sequence to the MATLAB, and we can directly get the value of this Fourier coefficients. Okay, so that's why this matrix multiplication is needed. Okay, so I hope this problem was clear. So now moving ahead, so the next problem is the transfer function of a discrete time IIR filter, that is infinite impulse response filter, is given by this. Okay, it means the transfer function of IIR filter is given to us. So now we have to determine and sketch the impulse response of the filter first of all, and after that we have to determine and plot the magnitude response of the IIR filter. Okay, so that that is basically the task here. Okay, so to determine the impulse response of this IIR filter, so we have to first of all solve this uh, h of z. Okay, okay, so let us first solve this. Okay, so h of z, that is the z transform of the uh, transfer function, or say uh, discrete time system, is given to us, h of z, which is equals to 0.12 z over z square minus 1 by 2 z plus 0.32. Okay, this is given to us. So now to solve this, what we have to do, we have to just uh, divide the factor of z, the divide z by in both the side. Okay, so h of z over z, we can write it as 0.12 over z square minus, yeah, this is 1.2. Okay, so this is 1.2 z plus 0.32. Okay, so now uh, here also we will use the same method, that is the partial fraction method, so as to solve this h of z. Okay, so why I am basically dividing this h of z with z, that we will see later. Okay, because see, in z transform we all know that z transform basically represented either as, let us say, for u of z. Okay, or say a of n into u of n. So corresponding to this function, the z transform is basically written as 1 over 1 minus a z inverse. Okay, so to write this transfer function in terms of z inverse, we first divide this h of z with respect to z, and later we will multiply this z uh, on both the sides, so as to get this uh, final expression in the form of z inverse. Okay, so that we will see later after solving this expression. Okay, so let us first solve it. So h of z, we can write it as 0.12 over, yeah, here z is there. Okay, so this is basically a factor of 2, which is z square minus 0.8 plus 0.4 z plus 0.32. Okay, so now you can factorize it. So the two factor will be z minus 0.8 and z minus 0.4. So these are basically the two factors. So now we can use the this partial fraction method. Okay, so as to basically determine the coefficient a and b. Okay, so now we will use the partial fraction method here, so as to determine the coefficient a and b. Okay, so this coefficient we already seen that we can determine this coefficient. Okay, so let us first determine the coefficient a, which will be equals to z minus zero point 0.8 into 0.12 over z minus zero point 0.8 into z minus zero point 0.4. Okay, so at z is equals to 0.8. Okay, so this term will cancel. So now once you plug this, okay, so this will be equals to 0.12 over 0.4, which will be equals to 0.3. Okay, so the value of A will be equals to 0.3, whereas the value of B will be equals to Z minus 0.4 into 0.12 over Z minus 0.8 to Z minus 0.4 at Z is equals to 0.4. Okay, so this will cancel, so that we can plug, and the final value of B will be equals to minus 0.3. So now we can plug the value of A and B in this expression. Okay, so this you can write it as 0.3 over Z minus 0.8. Sorry, this will be minus 0.3 over Z minus 0.4. So now we can multiply both the side by Z. Okay, so this h of Z we can write it as 0.3 Z over 0. Sorry, this will be Z minus 0.8. Okay, minus 0.3 over into Z minus 0.4. Okay, so now we can write it as 0.3 over 1 minus 0.8 into Z inverse minus 0.3 over 1 minus 0.4 into Z inverse. Okay, so now we can take the inverse discrete Fourier transform, okay, or say inverse Z transform. So the final expression of h of Z we can write it as 0.3 into 0.8 to the power n u of n minus 0.3 into 0.4 raised to the power n into u of n. So this is basically the final expression of h of n. Okay, that is the impulse response of the system. Okay, yeah, so here is the solution that we have seen. Okay, so this is basically the impulse response of the system. So we can now plot this h of k for various values of k, or if you have taken the parameter as n, so you can also plot h of n with respect to n. So here I am considering the time as a parameter of k. So h of k will be equal to 0.3, 0.8 raised to the power k minus 0.4 raised to the power k into u of k. So how to determine this, that we have seen previously. So now we are uh, plugging the value of k here as 0, 1, 2, and so on. Okay, so once you plug this value, so you can see that the transfer function of this IIR filter is this one. Okay, it is plotted like this. So from here also we can say, we can see that h of k, which is the impulse response of this IIR filter, that is infinite impulse response, is starting from 0 and goes to infinite. Okay, which is basically a response of IIR filter, that it is defined for infinite value of time. Okay, so this is basically a IIR filter. And one more thing that we can see here, that it is yeah, so this is basically the thing here, that uh, IIR filter is basically defined for infinite values. Okay, whereas the other kind of filter is also there, that is finite impulse response. So in the finite impulse response, so the transfer function for finite impulse response, if you plot it, so you will get that it is defined only for finite values of time. Okay, like this. And for other values of time, this will be 0. So this is basically a finite impulse response, whereas this is basically plotted for infinite impulse response filter. Okay, so now you can also plot the magnitude and phase response of this IIR filter. So here h of z that is given to us in the problem itself. Okay, so to determine the magnitude and phase response, we have to basically use this relationship between z and Fourier transform, basically, which represents the relation of z with omega. Okay, because basically we plot the magnitude and phase with respect to omega, that is frequency. Okay, so here we plug the value of z as e raised to the power j omega in the expression of h of z. Okay, like here. Okay, so after plugging this uh, value of z here in this expression, the final expression of h of omega we will get as this one. Okay, so now we can use this expression so as to determine the magnitude and the corresponding phase that we have seen earlier in a problem. Okay, so we will determine the magnitude of h of omega and phase of h of omega. Okay, so now we can plug the value of omega from minus pi to pi. Okay, so as to plot the value of h of omega. So once you plug the value of omega and plot it, you will get this kind of response, that is magnitude is like this. Okay, whereas the phase response is like this. So from here we can inference that magnitude of h of omega is basically having a value of 1 for omega is equals to 0, whereas for higher value of omega, that is pi, okay, it has magnitude almost like 0. Okay, so this represents that this is having a kind of low pass filter. Okay, because it is having a gain of 1 at lower values of frequency, whereas for higher values of frequency it is having a value of uh, 0, near about 0, let us say. So that's why this is basically a low pass filter, or say low pass infinite impulse response filter. Okay, so that is how we can analyze any kind of filter. Okay, so now moving to the next problem. So this problem states that implement the direct form, that is direct form 1 realization of IIR filter with the following transfer function. Okay, so for this transfer function we have to determine the direct form realization of IIR filter. Okay, so as we know that uh, direct form of realization of IIR filter. So to realize this, we have to basically know that how much delays are there, delaying element are there. Just a moment. Yeah, how much delaying elements are there, how much adders are there, and how much multipliers are there. Okay, so by using this we can realize any kind of filter. Okay, so like here we have to realize IIR filter whose transfer function is given to us. So first of all we have to know that how much delaying elements are there, how much adders are there, how much multipliers are there. So for determining these kind of elements, we have to first know the relationship between input and output. Okay, so as we know that for defining the relationship between input and output in a discrete time uh, system, we generally use difference equation. Okay, so first of all basically here we have to form the difference equation, and from that we have to determine this kind of elements. Okay, and then by using this kind of element we will realize this IIR filter. Okay, so let us now first of all find out the difference equation. Okay, so as we know that h of z is basically written as y of z over x of z. Okay, so this will be equal to z cube, or uh, yeah, z cube minus 2z square plus z over z cube minus 0.1 z square minus 0.07 z minus 0.065. Okay, so now what we will do, let me remove this. Yeah, so we can multiplying both numerator and denominator with a factor of z raised to the power minus 3. Okay, so once you multiply both numerator and denominator, you will get 1 minus 2 z raised to the power minus 1 plus z raised to the power minus 2 over 1 minus 0.1 z raised to the power minus 1. This will be, just a moment, minus 0.072 7z inverse minus 0.0, this will be minus 2, sorry, let me rewrite this. Z raised to the power minus 2 minus 0.065 z raised to the power minus 3. Okay, so now we multiply this. Okay, so we will get y of z into 1 minus 0.1 z inverse minus 0.07 z raised to the power minus 2 minus 0.065 z raised to the power minus 3, okay, is equals to x of z into 1 minus 2 z raised to the power minus 1 plus z raised to the power minus 2. Okay, so now we can take inverse uh, inverse df yeah, inverse z transform here. Okay, so we after getting the inverse z transform, we will get, after taking inverse z transform, we will get y of n minus 0.1 y of n minus 1 minus 0.07 y of n minus 2 minus 0.065 y of n minus 3 is equals to x of n minus 2 x of n minus 1 plus x of n minus 2. Okay, so now we can rewrite this as y of n is equals to x of n minus 2 x of n minus 1 plus x of n minus 2 plus 0.1 y of n minus 1. So basically I am trying to take this term on the right hand side. Okay, okay, so now we can write the remaining terms here, y of n minus 2 plus 0.065 y of n minus 3. Okay, so now by using this we can realize the IIR filter. Okay, so let us suppose this is basically x of n. Okay, this is x of n, that is input applied to the IIR filter. Okay, so this, so from this expression we can see that it is having two delaying elements apart from x of n, that is x of n minus 1 and x of n minus 2. Okay, so x of n given to us, so to determine x of n minus 1 we will use a delay element here, that is z raised to the power minus 1, and one more delay element will be there. Okay, like this. Okay, so here we will get x of n minus 1 and here we will get x of n minus 2. Okay, so now we will multiply this x of n, x of n minus 1 and x of n minus 2 with the corresponding coefficient that is given in this expression. So here we can see that x of n is multiplied by a factor of 1, whereas x of n minus 1 is basically multiplying by a factor of minus 2, whereas x of n minus 2 is basically multiplying with a factor of 1. Okay, so now we will sum up this. So for that we will use adder here. So one more adder will be here. Okay, so now we will add here. So up to this term we have got. So now to determine these terms, what we will do, we will first of all let us assume that this is my y of n. Okay, so here we will use a delaying element, that is z raised to the power minus 1. Okay, z raised to the power minus 1, minus 2 and minus 3. So total 3 delaying elements will be there at the output side. So let us suppose this is my uh, yeah, this is my delaying element. Okay, so from here what we will get, this is basically y of n minus 1, and here you will get y of n minus 2, and here you will get y of n minus 3. Okay, so now we will multiply this with the corresponding factors, that is 0 0.1, 0 0.07, 0 0.065. Okay, and now we will sum up these terms, okay, by using adders. So like here we will use the adders. Okay, so this is basically the final IIR filter realization. Okay, so from here we can see that this kind of direct form 1 realization requires 5 adders. Okay, so this realization basically requires 5 adder along with 5 delaying element. Okay, so here we can see that it requires 5 adder and 5 delaying element. It means that it requires more number of elements. Okay, so to further uh, reduce the number of element required to realize any kind of filter, we will further study, and from there we have found that by using direct form 2, so like here we have realized this for direct form 1. Okay, so after study we have found that by using direct form 2 kind of realization, we will further reduce the number of adder and number of delaying element required to realize any kind of filter, sorry, IIR filter. Okay, so yeah, so this is the next problem. Okay, so just a moment. So this is the solution of the previous problem, that is the realization of direct form 1. Okay, so that we have seen that this kind of architecture we will get. Okay, so now the next problem is the to implement the filter presented in the previous problem using the direct form 2 realization. So here we will now uh, use the another kind of realization, which is the direct form 2 realization, and here we will also see that the number of element requires to design the filter will reduce. Okay, so this is basically the mm, strategy here by using the direct form 2 realization. Okay, so now to realize the direct form 2 uh, kind of IIR filter, we will use the same expression of this input output relation. Okay, and by using this we will analyze or say realize the direct form 2 uh, kind of IIR filter. Okay, so for that what we have to do, we have to just interchange these two branches. Okay, so like here the output branch is basically uh, uh, present at the output of this filter. Okay, and the input part, that is x of n, x of n minus 1, x of n minus 2, is present at the input side. So now what we will do, we will interchange this branch with this, and vice versa. Okay, so as to get the direct form 2 kind of realization, so that we will do here. Okay, so like, if suppose this is x of n, okay, so, and yeah, this is my y of n. Okay, so first of all, as we know that here x of n, x of n minus 1, x of n minus 2, that is two delays are there. So let me first place the two delays here, that is z minus 1, z minus 1. Okay, so here you will get x of n, x of n minus 1, and here you will get x of n minus 2. Okay, so we will now multiply this with the corresponding factor, that is, yeah, that is 1 minus 2 and 1. Okay, and after that we will sum up this by using adder. Okay, so this this is the input part, whereas the output part, which requires basically the three delays. Okay, so here, as we know that we have already used two delays. Okay, so we will basically use one additional delay here, that is z raised to the power minus 1, and by using this we will realize it. Okay, so like, here here you have to just multiply this corresponding factor. Okay, so like, this is 0 0.1, 0 0.07, and 0.065. Okay, so the corresponding factor we have multiplied. So this is basically representing the direct form 2 realization of IIR filter. Okay, so from here we can see that this kind of realization requires uh, yeah, here I'm sorry, this, there will be a adder. Okay, okay, so here, although 5 adders are required, okay, but the number of delaying element required will reduce, so only 3 delaying elements are required. Okay, so here for direct form 2 realization, we requires only 5 adder and 3 delaying elements. Okay, so this is basically the realization of direct form 2 for IIR filter. So the another kind of realization is, uh, so here is the next problem, which is the, oh sorry, here is the solution of the previous problem, that is direct form 2 realization. So now the next problem is, implement the filter presented in the previous problem using the cascade form. Okay, so now we have to basically realize this same filter by using another technique, that is the cascade form. Okay, so to realize this, first of all we have to again go and see the transfer function, that is h of z. Okay, which is already given in the problem. So let me first write the uh, yeah, here is the transfer function, so let me write it here. So this is 1 minus 2 z inverse plus z raised to the power minus 2 over 1 minus 0.1 z raised to the power minus 1 plus sorry, this will be minus 0.07 z raised to the power minus 2 minus 0.065 z raised to the power minus 3. Okay, so cascade form means you have to use sub sub filter kind of structure, and then connected in series. Okay, so this basically represents the cascade form. Okay, so for that we have to first factorize this, okay, in a single order form or double order. Okay, and after that we will uh, uh, get the sub uh, or say uh, a small part of these filters, okay, that we will connect in this series. Okay, so let me first factorize this. Okay, so this denominator, as we know that this denominator is having a degree of 3, so it contains only 3 roots. Okay, so that you can factorize it later, so I am directly writing it here. So the after factorizing it, you will get 1 minus 0.5 z raised to the power minus 1 into 1 minus 0.2 plus j 0.3 z inverse into 1 minus 0.2 minus j 0.3 z inverse. Okay, in the denominator, whereas in the numerator this will be 1 minus z inverse into 1 minus z inverse. Okay, so now we can see here that numerator is having a real poles, real zeros, whereas the denominator is having uh, real as well as imaginary poles. Okay, so one more thing that we have to consider here, that the filter that we are realizing here is basically realized only for real values. Okay, it is not realized for the complex values. Okay, that we have to consider, take it here. Okay, this thing that we have to consider it here. Okay, so to eliminate this imaginary poles, what we will do, we will multiply this. Okay, and then rewrite it as 1 minus 2 z inverse plus z raised to the power minus 2 over 1 plus 0.4 z inverse plus 0.13 z raised to the power minus 2 into 1 over 1 minus 0.5 z raised to the power minus 1. So this basically shows that h of z is basically realized by using multiplication of these two uh, transfer functions. Okay, so we will first try to realize these two kind of transfer function individually, and then we will connect these two in series. Okay, so as to realize the cascade form. Okay, so let us first try to realize this part, that is the first part. Okay, and then we will go for the second part. So to realize the first part, let us suppose this is basically my x of n. Okay, so it is having three part, that is x of n, x of n minus 1, x of n minus 2. So we require basically two delays here. Okay, we require two delays so as to get x of n, x of n minus 1, x of n minus 2. Okay, so now let us multiply the corresponding factor. Okay, so this is 1 minus 2 and 1. Okay, and then later we will sum up these factors, these signals. So this we can directly connect. Okay, so this is basically the input part. Okay, and output part, or let us suppose we are realizing this by using uh, direct form 2. Okay, instead of direct form 1, we will realize this by using direct form 2. So this requires basically two delays. Okay, so this is 1 minus 2 and 1. Okay, here is the adder. Okay, yeah, so Similarly, here also we have to use adder. Okay, so this factor also we have to write, like here this will be 0.4, this will be 0.13, sorry, this will be minus basically. Okay, so after that, so this is corresponding to the first transfer function. Similarly, we can determine the for second transfer function. Okay, so let me draw it. So this is y of n. Okay, so y of n is basically, sample it here. Okay, so this is basically y of n minus 1. Okay, and this will be multiplied by yeah, 0.5. Okay, and then add it here. Okay, so this is basically the realization of the IIR filter using the cascade form. Okay, so that's how we can analyze any kind of filter by using this different realization technique. Okay, so some of them are, we try to cover it here. So here is the solution of the problem that we have seen. So this is the individual part that we have seen, and then this is the second part, and then after connecting these two in series we will get the cascade form. So this was the last problem, and thank you all for attending this session.